this is going to be about CPU idle, which is, first of all, I maybe talk about it a bit, like what it is, what it does. So if there's no other tasks to run on the CPU, the idle task runs. The code for the idle task is called the idle loop, and it calls CPU idle to let the CPU enter an energy saving state, basically, if that makes sense. It uses so that there is, the main loop, and there are governors and modular, so you can use one of the governors or the other depending on the needs or your taste or whatever. The governors decide which idle state to put the CPU into, or which energy saving state. So the terminology I will use is idle state means an energy saving state of the CPU. Okay. There are 3 governors in the main line. 2 of them are practically used and relevant, which are menu and CEO. And their idle states are defined through 2 parameters each. One of the parameters target residency. This is the time the CPU needs to be in the idle state so that it makes sense to put it into that state. And exit latency is obvious, right? How much time it takes to wake up the CPU from that state. That's the whole thing. And it's very straightforward. It is per CPU. It only is used when the idle task runs on that CPU. It generally doesn't take other CPUs into account unless the driver, which is then used to actually put the CPU into the idle state, coordinates somehow between CPUs. But okay, so what's the problem? What's the problem with it? The problem is that the governors don't really take latency into account. They just go for maximum energy saving. And if you want the latency to be taken into account, you need to use PMQoS or CPU latency QoS in the latest terminology. But this is a hard limit. This is a hard limit, and it prevents the governor from selecting state deeper than X, which is so the value you put into QoS is the maximum is the maximum target exit latency that you can tolerate, basically. However, the interface is either per CPU or global. So if you are, and the per CPU interface is in sysfs, which means that it's not very suitable for tasks to use in particular. And somebody needs to write a value to a sysfs file. And the interface, which is based on a special device file, is global. So if you are a process and open this file and you write the value there, you affect all of the CPUs in the system. That's not very convenient or suitable in many cases. And that there is no other way to take latency into account in the current governors. But there are use cases in which latency is important. You want tasks to run on idle CPUs and wake up them quickly in some cases. So maybe they should not be put into very deep idle state then, and so on. But there's like the PMQoS is the only way to provide that information to the CPU idle subsystem. So it is taken into account. So there was an attempt to use utilization in the TO governor to kind of figure out the latency piece. But I'm not considering it as a success, to be honest. No, we are there is a discussion in the mailing list about this, right? So maybe adjust it and even drop it entirely because it is not clear if it helps that much, and maybe it hurts more than it helps, sort of. So I thought about it, and I just had a few like kind of disconnected ideas about how CPU idle can be improved along the lines of maybe taking latency into account in a more significant way. Okay, so it's just a bunch of ideas. So I will use the remaining time to just toss those ideas at you and then see what happens. Okay, so one of the ideas is in a TL governor, it's kind of easy to reset the statistics when the utilization changes, which to me would make sense because then if the utilization changes, this means that the expected pattern of wake-ups probably changes as well. So the statistics collected so far may not be applicable anymore. And now, of course, if this happens, then we need to wait for some time until the old statistics are replaced with the new ones, and then from that on, they are useful again. So maybe we should just say, hey, if the utilization changed like by 50%, so we drop the old statistics and start to collect them from scratch. One idea. Good, bad, ugly.
You might have a problem where people want the utilization to change faster and faster than right now. So which means that from one idle to another one,
this is no. This is only observable when the governor runs. It is not observable otherwise by the governor, right? So it only can see the utilization at the times when it runs.
No, but I mean right now, some people complain that we need 200 and something to go from 0 to max. They would like to decrease that to maybe 100 or 50 milliseconds. And at that point, I mean, if in 50 milliseconds you can go to the full range, I don't know if maybe that can become too quick for you.
Yeah, to adjust. Okay, fair enough. But all right, another thing is that, okay, so what about this utilization heuristic that is there? Maybe it can be adjusted. So one obvious idea is to change the threshold. Well, the threshold is bad anyway, because it changes the behavior in a binary way, kind of arbitrarily, because it doesn't, you just need to guess what the threshold to use, and it is a single value. So, you know, there is no way it will fit everybody. So that's not a particularly fortunate design, but it may be adjusted. It may be done like in a gradual way based on a utilization by, say, by making the governor select shall idle states more often if the utilization is high or something like that, kind of automatically. That can be done. We can just drop it. I guess it's a matter of testing at this point, right? What is the better thing to do? Can be done. So yeah, another idea is, well, we use the polling stage on x86 to address the cases when there really is no idle time, at least from the governor perspective. And then in that case, it doesn't even make sense to ask for C1 because that's pure latency, because then if we wake up again and then then it doesn't really help, right? So that's one idea to consider. In the cases when there is a lot of stuff happening very quickly, it may help to reduce latency. Yeah, this kind of is connected to what we talked about in the previous slide. Like if we have this QoS interface, it can be used to as a kind of sub QoS variant that will again cause the governor to select shallow idle states more often than the deep idle states if the QoS is indicating that. All right. And another thing related to QoS. So if you say that there is a there are tasks that are latency sensitive, say, so wake them up on CPUs that are not in deep idle state. This is more about like CPU idle at large than the governor. But currently what happens is that if the scheduler finds an idle CPU, it will try to run the task on it, regardless of what idle state the CPU is in, which makes which is kind of problematic because if it happens to be like in a deep idle state, the wake-up latency is large, and then the task will see this like in its wake-up latency. So maybe for those tasks, it's better to just find a CPU that's running or in a shallow idle state and wake it up on that CPU instead of the deeply idle CPU. All right.
What about setting a timer? So we wake up the CPU ahead of what is before, so with the exit latency. So we wake up just before.
That can be done.
So it should be wake up at the moment we want him to be wake up. So there is these latencies.
That can be done for idle states, except for the deepest one, because in the deepest idle state, you might want to stay forever. So that will break the power numbers for many systems.
Okay, but
and if the idle state the governor Daniel, in addition to deciding what idle state to put the CPU into, the governor also decides whether or not to stop the scheduler tick. And for a shallow idle state, it doesn't stop the scheduler tick. So the tick will wake you up anyway at one point. So that timer thing could maybe help in some cases, but you know.
It won't help in deep states.
No,
It can't work for sporadic wake-ups because you don't know when it's going to happen. I mean, it only if you know that the task is going to be woken up by a timer, you could arm the timer early.
But I guess the point is that if you select say C1 and you know but then you may burn some energy by just looping around this idle state, right. And you wake up and then go idle again and wake up and go idle again, and
I think that doesn't make sense
until you actually have something to run.
Your observation to actually be smart about selecting which CPU we wake up, that's probably better,
right? And it may be necessary in some cases. It may be necessary to reserve a CPU such that you only put it into, say, a shallow idle state, so that if you have a task that has to wake up quickly, you will run it on the CPU, right? On a specific one.
I would
like that.
Argue against what Thomas said, and I think because we want to be, first of all, we want to be waking CPUs up if new tasks come, right? We don't want to pack usually or often, sometimes anyway. And plus, I mean, the task also benefits if it gets a CPU on its own, or in some cases anyway. It's got to be a pretty complex heuristic to implement this, right? Or what is it then?
I don't think it's heuristics. I mean, if you wake up a task and you have capacity on the already running CPUs, that's a no-brainer. You keep it there. If it has constraints
that's the easy case, actually.
in terms of latencies, where you have to or you have a capacity problem on the already running ones, then you have to pick one. But then if you have the proper information, which ones or in which idle state, and you can pick the shallowest one.
Yeah.
So the information is, we all have the information available, we just don't use it.
So during the initial task wake up, we do that. We select the shallowest idle state to place the task on. It's just that during the regular task wake up, we go the fast path and we don't iterate to that. So it shouldn't be very hard to try that out.
Yeah, that's so Julia was. Oh, okay. Well, all right. So I think we can. If there are no more comments or questions, these are just the ideas to consider.
But isn't the fast path line, we take the first idle CPU, right? And if we would look for the shallowest idle state, then we have to traverse all the CPUs in this. That's why it's called fast path, right? And slow path.
So instead,
you can find the better CPU in terms of shallow idle state, but then you have to look more.
Yeah, but then we can create like an additional data structure for that. And
it's
then,
not necessary. It's just the time you have to, to find this shallowest idle state. It's much more time than to just pick the first idle. When you have like a large shared domain, 64 or even higher numbers of CPUs.
Yeah, but then if you have, say, a list of CPUs in C1, say, then you can pick the first one from that list. Just as well, because you are guaranteed that it's idle at that point. Right. Something like that, yeah?
Yeah. What you really want is you want to know what the wake-up latency is going to be if you put it on a task on a CPU which is already busy. That's really expensive to work out. But you need to know that to know whether you are better off putting it there than on a CPU for which we know the exit latency because we have the stats for all the idle states. So maybe we need to figure out how to calculate that.
That's a fair point, yeah. So technically this is easy, but yeah.
Actually, it's quite
you
hard.
Might not, yeah. No, how much time it will really take to wake up, right? In this case.
It's quite hard with the current information and how we store the data. So we have to be smart. If we want to get smarter in the decisions, we have to just come up with better storage. But it's all about data structures. So not about the implementation details. So you have to sit down and say, hey, how can I effectively, efficiently represent these bits of information in a very quickly accessible way? It must not be perfect. So that one problem I noticed with all of this is people try to do perfect. Perfect is wrong. Perfect is the enemy of good. So what you want is something, it's 95% of the time it's correct. It's a bitmap. You can find, or an array of bitmaps or a hash or whatever. You can find shit pretty fast. If you find out, I picked the wrong one because the other CPU just went one state deeper. So what? I mean, that's not the end of the world. But you get it in 95% of the time. You get it right with the estimate.
Yeah.
And then you won, and you don't inflict a full linear search over whatever in the wake up path, because then the people who really care about wake up latency will hate you.
Yeah. So
the problem is really that the data structures we are using today are not suited for any of this.
Right. There's one more side to this. So you can actually reduce the lookup in the scheduler if you have the data structure like that, because then you are so a CPU cannot be more idle than a CPU in an idle state, right? So you can just pick one that's in the slowest idle state and be done, and without doing the search at all. In fact, yeah. All right, so we have no more time, I guess. Last question maybe, and then we can conclude. The internal throttling, yes. Right.
Yeah, so last question. Can we start from clean room implementation instead of hacking the existing governor?
What do you mean by clean implementation?
Like this from this clean ground. So instead of fixing this TO
Okay.
stuff and
So what
then,
do you mean by clean implementation?
starting from getting the requirements for the new governor from scratch, which would be aligned with this QoS interface and maybe those new data structures.
Okay, that's fine, as long as your governor will be sufficiently different from the existing one.
Well, it deserves actually, if you want to link this QoS chain, then
I'm not sure. Okay. Yeah. 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 Thanks a lot.
Again, we did it.